Now let's turn to some bonding theories. What we're going to do tonight is start talking about the different types of bonding theories that are seen in coordination compounds. We're going to talk about really three different types. We're going to talk a little bit about the Lewis acid-base definition. I'll briefly mention valence bond theory, and then we'll really work with crystal field theory mainly. First, there are truly four different bonding theories that we look at when we deal with coordination compounds. There's the Lewis acid-base definition, where you've already seen this, that ligands have lone pairs of electrons, and those lone pairs of electrons interact with a metal cation that has empty d orbitals and form a coordinate covalent bond. This idea is based upon Lewis structure, so it's a very simplistic idea on how bonding occurs. Second is valence bond theory. This idea was proposed by Pauling, and it uses hybrid orbitals. You remember hybridization from organic chemistry to explain bonding and structure of the molecules. It still works well for very simple molecules, but really it doesn't work. We don't use it much in coordination chemistry today. The third type is crystal field theory. This is an approach where we think of the ligands having those lone pairs of electrons. Those electrons are negatively charged, and they're coming in and they interact with a positively charged cation, or a positively charged ion. This electrostatic approach is the way we're going to focus on mainly in this talk for understanding bonding and coordination compounds. Ligand field theory is very similar to crystal field theory, just slight differences. Ligand field theory uses molecular orbitals to describe bonding and coordination compounds. However, there is some overlap in the terminology between crystal field theory and ligand field theory. Now let's talk a little bit about Lewis acid-base chemistry. Let's start out by thinking about cobalt 3+. So there's the cation. We know that it has empty d orbitals that can accept lone pairs of electrons from a ligand. So we bring in 6 ligands. We'll make them amine ligands. And they come in, and those lone pairs on the nitrogens interact with the cobalt d orbitals and form coordinate covalent bonds. So we think of the CO3+ as the Lewis acid. It accepts electron pairs, and it contributes 0 electron pairs to the coordinate covalent bond. However, the Lewis base is NH3, and it's the electron pair donor. It contributes 2 electrons to the coordinate covalent bond. So both electrons in this case come from the ligand to form that bond. Now, when we think of Lewis acid-base theory, we think of CO3+ as the Lewis acid, as we've talked about, NH3 as the Lewis base, and so we form this coordinate covalent compound shown here. Now there's a special name for the product of a Lewis acid-base reaction, and that's known as an adduct. We call it a coordination compound, but you can also see the term adduct. By definition, it's just the product of a Lewis acid-base reaction. Now, if you remember when you drew Lewis structures, there was a simple rule for seeing if you could draw a good Lewis structure, and that was the octet rule. That stated that generally, and it didn't work in every case, that if you can surround an atom by 8 electrons through lone pairs and bonding pairs, that is a good Lewis structure. Or that's something that the atom wants to do. It wants to have 8 electrons around it. Now, in coordination chemistry, there's a parallel rule, very, very similar to the octet rule, called the effective atomic number rule. It's easy to calculate. You take the numbers associated with you take the number of electrons associated with the metal cation, and add to that the number of electrons contributed by the ligands. You add them together, and if the effective atomic number, EAN, is equal to the number of electrons for the next higher noble gas, then it's probably a stable coordination compound. Now, much like the octet rule, the effective atomic number is an indicator of how stable a compound is. Also, like the octet rule, stable compounds are formed where the octet rule is violated. So, you should believe that when compounds violate the effective atomic number rule, they can also form as well. There's exceptions. The effective atomic number rule works best for organometallic compounds. Those are coordination compounds containing direct metal cation carbon bonds. So let's look at an example together, and what I would like you to do is work through this example on your own before finishing this video, so stop it when you get to this point. Try calculating the effective atomic number for the following coordination compounds, and then tell me which of these compounds obey the effective atomic number rule. The answer is found this way. So cobalt 3+ has 24 electrons. Neutral cobalt has 27, but since it has a 3+ charge, it loses 3 electrons, giving 24. Each ammonia contributes 2 electrons to the coordination compound. So 6 times 2 is 12 electrons from these 6 NH3s. 24 from cobalt plus 12 from NH3 equals 36 total electrons. For NiCO4, nickel is metallic nickel here, so it has 28 electrons. And each CO contributes 2 electrons to the bond, so 4 times 2 is 8. 28 plus 8 is 36 electrons. WCO06 is the next one. Now, once again, we have neutral tungsten, and neutral tungsten has 74 electrons. CO has 2 electrons that contributes to the bonding, but since there's 6 of them, we must multiply 2 times 6 to get 12, and 74 plus 12 is 86. The final example, we have chromium 3+, which a neutral chromium atom has 24 electrons, but as its 3+ cation, it has 21 electrons. It has 6 NH3 ligands, so the ammonias contribute 12 electrons to the bonding, giving you a total of 33 electrons. So, of these 4 compounds, there's only one that violates the effective atomic number rule, and that is D.